Good day, everyone. Today I'm going to speak with you about atomic and molecular structure. Welcome. Okay, so first thing is we're going to get into the definition of what exactly organic chemistry is, why carbon is really sort of the central element in all of organic chemistry, the main group elements and valence trends, so just a little bit of a review of periodicity, formal charges, ions, and ionic compounds. What those all mean is, going forward. Line structures and obeying the octet rule. So now, you've seen some organic molecules, at least from Chem 1 maybe, and a little bit of Chem 2. But we're going to have to devise a way in which we can draw things shorthand and in a quick manner of time because there's just way too much to cover in this course. And then resonance stability, so not just general examples, but organic chemistry examples as well. So I'll show you some exercising or exercises in electron pushing. Okay, and then finally we're just going to review a few functional groups to get you kind of acquainted with those. Just really more of a memory game than anything. Okay, so let's start off with the study of organic compounds, carbon-based materials. So carbon has very strong bonds with pretty much any other element, so that makes it particularly attractive. It can branch, right? So you don't see oxygen bonding to other things, right, in a tetrahedral form as a central element. You're going to only see that with carbon, right? So you can see that with silicon, but silicon is going to be a little bit more electropositive than carbon. So in other words, for things like, let's say a fluoro group or any other compound, any other electronegative element that's directly attached to it, it's going to have more of an ionic than covalent interaction. So ions are good for being stabilized, electrostatically as opposed to covalent structures, which are much more abundant. Okay, so as you may or may not know, as you tack on more double bond or more bonds, so there's first the 1 sigma, then 1 pi, and then an additional pi for a triple bond. As you tack on more bonds, the more stable that particular nucleus to nucleus interaction is, right? And therefore, the more electrons you tack on, while this seems sort of counterintuitive because electrons tend to repel, they're actually going to draw those nuclei closer together, right? So, you can consider, let's say, CC single bond is going to be pretty long, right? Well, there's just because they have 2 electrons to whiz about and form the sigma bond, right, between the 2 nuclei. So it's going to be hybridized, which we'll get into hybridization later in the course. Then we'll see that if you have an additional bond there, so a sigma and a pi bond, you're going to have a little bit of a tighter knit community, if you will, between those 2 carbons. So there's going to be less of an ability for other electrons to kind of butt in and from another nucleus and form a bond that's alien to what you see here. Okay, and then a CC triple bond is going to be even shorter, right? So it's basically 2 pi bonds that are perpendicular to one another that have kind of shrunk wrapped those 2 carbons even closer together. Okay, so the bond that's going to be existing in all of these is going to be the sigma bond. All right, so that's going to be lowest in energy, so then the next pi bond is going to be slightly higher in energy, and then that second pi bond is going to be in equal energy to that first pi bond. Okay. So some examples of organic products or organic molecules. For instance, amino acids, right? So these are things that you can ingest. These are things that are synthetically made that you probably don't want to ingest. Then there's other things that we take advantage of every day, like plastics, right? So something that's a polymeric and based, so polyethylene, polypropylene, PVC or polyvinyl chloride, as you might have heard. And then there's also hydrocarbons. So some pretty elaborate, let's say C8 structure, which is going to be what you fill up your gas tank with, right? So it's primarily of octane, a high percentage of octane, right, with some distillates that have carried over. So why exactly carbon? Again, branching is important. It's kind of a sweet spot in terms of electronegativity. So there are ways in which it can be very much manipulated, and the more carbons you tend to tack on, the more grounded that particular structure is going to be. So we'll get into some intermolecular forces later, but if you just take something like CH4, right, that's going to be a gas at room temperature. So methane gas is going to go airborne at a very high speed, as opposed to something like wax, which is C30. So that's going to be CH3, and then multiple repeating units of CH2. So this is going to be a linear compound, and you may have some branching of that too. But when I say linear, it's just going to be a straight chain zigzag, which I'll show you later. So VSEPR, or electron repulsion, is really going to make that sort of zigzag motif happen. Because again, if everything's going to be tetrahedral in geometry, you want everything spaced out to the best of its ability. Okay, so what else in terms of other groups? So we've talked about carbon. What about the other ones? Well, thankfully in this course you're just going to be mostly concentrated on the main group elements. When I say main group elements, I already kind of cut out the part of the periodic table you need to be most concerned with. So notice that carbon is sort of like the no man's land in terms of what's electropositive and what's electronegative. But you'll see that there are possibilities of carbon carrying a negative charge as well as a positive charge. Now, these aren't things that you exactly pick up out of a bottle, but they are what are going to be referred to as intermediates. Okay. Now, let's review some other species here, not just carbon. So hydrogen can go into the +1. Anything that's in group 1A is going to be losing one sole valence electron. So if you remember, with the main group elements, whichever group number it is actually positioned in is going to tell you exactly how many valence electrons are going to be on that outer sort of orbit, if you will. Okay, so aluminum can lose 3 electrons, magnesium can lose 2 electrons, sodium can lose 1 electron. So those are all within period 3 rather, but they're in groups 3, 2, and A respectively. So, 3, 2, and 1A respectively. Okay, and then on to the other side where things are more electronegative. Remember the trend for electronegativity. So E negativity about the periodic table is going to go up and then to the right. So in other words, pretty much diagonally across, going right and up. Okay, so that's where increasing electronegativity is going to be about a particular periodic table. So your fluorine, your oxygen, your chlorine, those are going to be the most electronegative elements. So what that means is those are going to be the elements that are going to draw as much electron density as they possibly can from other things in which they're attached. Okay, so you can see that oxygen can be charged as O2 minus to fill up that full octet. Cl minus, you've seen before with sodium chloride, right? Cl minus is going to be a full octet. So we think back to our Lewis structures. this is going to be a full octet because there are 8 electrons surrounding that one chlorine. Okay, so that's a stable anion. Just like O2 minus is a stable anion. Right? 2 minus because it has the 2 additional electrons surrounding that particular nucleus. Now, just as a quick concept check, which one of these particular particle counts assumes the identity? Well, it's going to be the proton count. So the proton count is going to tell you, you can have some extra neutrons, etc., but really it's the protons that's going to tell you what the particular element is, right? And then the negative charge and positive charge. The negative charge is going to indicate that there's going to be a surplus of electrons relative to protons. If there's going to be a positive charge, that means there's a deficiency of electrons relative to protons. Okay? So just a little bit of review there. Now, I talked about the octet rule. Let's talk about electronegativity and then dipole moments. But we're going to get into Lewis structures. So these are Lewis symbols, not Lewis structures. And these are just molecular formulae. All right. So let's take these 2 examples that I have in the notes that you should have to follow along. Okay. Anybody out there point out a different or something that may not stick? Well, it's a little bit concerning here that this carbon has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons whizzing about it at all times, seeing as that's over a full octet. Okay, so remember that you can't have an expanded octet if you don't have those D subshells that you can dig out from and form some bonds that way. So whenever you see expanded octets with phosphorus or things like that, they usually have a D subshell that they can borrow some electrons from. So we're just dealing with S and P subshells to make some kind of hybridization, right? So in other words, the sigma bonds and pi bonds that I alluded to before, those are all going to be hybridized bonds. Okay, so in other words, this isn't going to fly, all right? This is not a satisfactory Lewis structure. Again, there's beyond a full octet there. Okay, so let's look at another example here. Okay, so remember that nitrogen has a lone pair and is typically bound to 3 different things in the ground state, or 3 bonds in the ground state, whatever. So right here it looks okay. What's concerning here is that there is no charge and we don't see any lone pair. So in other words, we need to calculate a formal charge. So sort of back of the envelope calculation here. Formal charge subscript N for nitrogen. That is going to be formal charge, valence electrons in the ground state is going to be 5. Okay. Minus how many bonded electrons are around it? 1, 2, 3, 4, 5, 6, 7, 8. So 8 divided by 2. Okay, and then we have how many lone pair electrons? Nada. So in other words, that charge is going to be +1. So in other words, we need to put a formal charge right there. By the way, at all times I am going to denote that I'm going to be circling every type of charge that I have. Okay, so just be mindful of that. So this particular charge has to be there. Now you'd need something there to counter the charge, right? No charge can just exist on its own. There needs to be some kind of counter charge because this would be otherwise very unstable and have to react with something else. Not to say that other anions and cations can't interact with other things somewhere down the line, but we're just trying to learn to crawl before we can walk here. Okay, so now that we have sort of electronegativity back in our brains here, let's think about polarity. Okay, so this is something we're also going to revisit in chapters 2 and onward. But if we think of a dipole moment is going to be where there's an electron deficiency and an electron surplus on one end and the other. Okay, so I'm going to draw this pretty elaborate structure here. This is just going to be nitrobenzene. Okay. So notice how this is kind of taken me forever to draw. That's because this is not a line structure. Okay, so let's just double check our work here. We can look and see around this entire ring that carbon has 1, 2, 3, 4, 5, 6, 7, 8 electrons surrounding each one. Now the only exception for the octet rule, aside from your expanded octets, is the duet about hydrogen, right? So there's only that one s subshell that hydrogen has. So in other words, it can only hybridize with something else and form a duet. So there are no more protons there to drag more electrons around it. Okay. So we're good all about the ring. Here we have nitrogen. Again, nitrogen is bound to 4 things, has the full octet, but does not have a lone pair. Okay, so that means that based on our previous formal charge calculation, that's going to be positive. Is this going to be positive? No, because we have 1, 2, 3, 4, 5, 6, 7, 8, and oxygen is electronegative, remember, so that's stable. We also have 8 electrons surrounding this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. However, there's only one bond attached to that oxygen. Oxygen is much more stable when it's bound to 2 things or doubly bound. So here we do the formal charge calculation of oxygen. So oxygen has 6 valence electrons in the ground state. Remember, it's in group 6A. Okay, so 6 minus how many lone pair electrons? 1, 2, 3, 4, 5, 6. So we'll put that in the end. How many bonded electrons? 1, 2 divided by 2. So that's going to be 6 minus 1 minus 6 is going to be -1. So we're going to put a negative charge right there. Okay. So in other words, I'll erase that calculation. What you see right here is that this particular compound is net neutral, right? So the negative and the positive are cancel one another out. This is what is referred to as a Zwitter ion. Okay, so if you've seen previously in your general chemistry education, remember that all those nitrates are fully soluble in water, whatever nitrate you have paired up to whatever cation. So that nitrate is going to look like so. Okay. So remember that particular particle is a polyatomic anion, but it's still a particle, right? Because if it's missing an electron that, or it has a surplus of an electron like it does here, that means it's a negatively charged unit, right? Particle. So positive to negative are going to cancel one another out, and then you're just going to be having a negative anion on one of the oxygens at any time. Now, can these electrons just kind of flip about? You betcha. Right? So these are going to form resonance structures. So this can also resonate with everything in the ring here. We just haven't really gotten into that just yet, but we will. Okay, so back to our dipole moment before I draw this other resonance structure here. Okay, so ring around the rosy ad nauseum, you're going to see this sort of migration of electrons going from one oxygen to the next and pushing them about. Okay, so one other thing about dipole moments. So we have an electronegative benzene ring that's right here. Okay, again, this is what is referred to as nitrobenzene. This ring that you see right here is going to be electronegative itself. So as you add more bonds onto in between two particular elements, the more electronegative that particular section of the molecule becomes. But notice how you have two oxygens, which are almost second to most electronegative next to fluorine, up there at the top. So it's going to want to draw electron density away from that ring over towards that nitro group right there. So this is what is referred to as a nitro group. Okay. You'll see some nomenclature about these in Inner Chapter A, which is the next chapter over. Okay, so, but back to drawing that dipole moment. So it has to go from something that's slightly more electropositive to something that's more electronegative. So it's a drift up of where electrons are going to be more likely to populate. Okay. All right. So I've kind of gone over some formal charges with you already. Let's go over another example with dipoles. So dipoles can cancel one another out as well. So if you have, let's say, this dichloroalkene, where both of these chloro groups are up at the top, and then these electron deficient hydrogens are down at the bottom, you have a little bit coming out of here in this direction, a little bit coming out of here in this direction. But if it's a vector quantity, these two have to sum up together and come up at the top. So in other words, the net dipole moment will go straight up, 12 o'clock. Okay. Now, if you had a chloro group down here on the opposite end, you'd have a cancellation of a dipole and it would be net zero. So in other words, directional really kind of makes a difference here. So again, we're going to swap out where our chloro groups are relative to that pi bond, right? So in other words, these are what are referred to as stereoisomers of one another. This would be cis and this would be trans. Okay, so if you have those two fighting for the same electron density, they're basically just going to cancel out. Okay. All right, so we talked about some ions a little bit. Showed you some particular elements that had formal charges in a particular larger structure, right? So there are some examples in which you'll have acids that ionize from splitting apart. You have bases that are already ionic, and they can take some hydrogen away from something else. And then you also have catalysts, right? So Lewis superacids, if you will, like aluminum chloride or BF3, or even something like mercury acetate, mercury 2 acetate. Okay, so just a little bit of a conceptual review. What is the relationship between acetic acid, and line structure drawing mode? Okay, so this is a Lewis structure of acetic acid. What is the conjugate base? Well, it misses that H plus, so it loses this one right here. It's going to go to an acetate. I got this right. I swear I'll get this right. Okay. Now, what we see here is an anion, right? But is it a stable anion? Yes, it is. Because these lone pairs can actually flop on down and push these electrons over to where they're on the top now. And you have a double bond here at the bottom and a single bond on the top. So these are going to constantly kind of pendulum back and forth these extra electrons that are came from this pre-existing bond here. When hydrogen got H plus, got picked up by some kind of basic species. We'll say just OH minus or something like that. Just textbook example of a base. Okay, so with this resonance structure, akin to the one that I drew earlier with a nitrate, with more resonance structures, and this is the another one of your general chemistry examples, the more stabilized that particular ion is, right? So it's going to fluctuate back and forth. You're going to have some kind of resonance hybrid that's really going to look something like this. Okay, and then that negative charge right there. So in other words, this isn't sort of like a freeze frame where you can have it here and then, a couple minutes later it's going to come back this way. No, it's constantly going to be cycling very fast. Electrons just happen to move at, typically the speed of light. So things are going to move at quite a high speed. Okay, so this is what is referred to as a resonance hybrid. If you were to draw out all the different resonance structures, let's say if you had a more elaborate construct, you would just put this here in sort of brackets, if you will, before you had something that was stabilized. But if you were just to draw a general looking resonance hybrid, this is what it would look like. Okay, so let's look at some organic examples of things that have formal charges. Now, you've noticed here that if oxygen just has one bond connecting to it and it has an additional lone pair, then it's going to be negatively charged. It's a formal negative charge. Okay. Let's take something like betaine hydrochloride. Okay, so this was once actually marketed and sold as a supplement. Maybe it still is, I don't know. Okay, so this is also an existing zwitterion, right? So it has a positive and a negative charge to be net neutral. This is analogous to an amino acid that is very simple in nature, referred to as glycine. So in other words, instead of having all these methyl groups, so the CH3 here is a methyl group, attached to nitrogen, you're just going to have NH3 instead of N with 3 methyl groups attached. Okay. So you can see a more accurate representation at neutral pH. So neutral pH is going to make sure that this particular oxygen is going to stay deprotonated. For reasons we'll get into later, this is going to have a pKa of about 5, if you remember what a pKa is. Okay, so why is all this relevant? Well, these positive formal charges should be taken into account. Because oftentimes you're going to see some intermediates in this course, and make no mistake, when we get into mechanisms and things like that, all this is going to make all the difference in the world. So you really have to pay attention to your formal charges and things like that, or you're going to get lost really quick. Okay, so to identify an ionic bond, right? Let's say if you wanted to keep this as a salt, let's say if this were, let's say this particular example right here, if you wanted to keep that stabilized, you would need to have a sodium plus or a potassium plus or something like that to make sure that this wouldn't, it can't just exist on its own. It needs to have something to counter the charge. So either the hydrogen that was originally there, H plus, or some kind of group 1A element. Or it may be tacked on to multiple iterations of it might be attached to, let's say, something that was a divalent or trivalent metal. Okay. Okay, so when you think of electronegativity, you can go to this particular website, ptable.com, and you can look at a periodic table and you can see all the different sort of intrinsic properties and click on electronegativity, and you can look at which value is for each particular element. It's very comprehensive and thorough. Whenever you have a change in electronegativity is greater than 2, that's going to be an ionic bond. So if it's less than that, then typically that's going to be a covalent bond. Remember that there's such a disparity in electrons where a ionic bond is really electrostatically attracted. So that means one has to have excess and one has to have nothing. Okay? Or maybe not nothing, but there's no charge over there on the outside where the valence electrons should be, or no electrons there. Okay, so let's see if we can spot some ionic compounds for these 3 examples that I've given to you. So we know that C6 and 8, or C6H6, that's going to be just regular old benzene. So that can't really ionize unless you have an extremely strong base. And it won't stay as an ion. For very long. Okay, so C6H6 is going to be benzene. And here I am cutting to the chase and going straight to line structures. Alright, so line structures are simply going to be every one of these corners that you see right here are going to be represented as carbons. Okay, so remember, to have a full octet about a carbon, you need to have 4 bonds attached to it. So you only see 3 here that are visible. So that means that each one of these hydrogens is just going to be assumed. Okay, so if you're unclear as to what the octet rule is, you better get clear on it. Okay, so is this going to have any type of ionic bonds? No, because if you look at hydrogen to carbon, which is the only 2 species you have, there's not an electronegativity difference to merit having an ionic bond. So no ionic bonds. So just covalent bonds, just all around the ring. Okay. Now, here's another example, sodium phenoxide. Okay, so this is what sodium phenoxide is going to look like. I'm just going to draw the Lewis structure here, and I'll go over some more examples with line structures in a minute. Okay, and then I also want to put my double bonds there to fulfill that full octet. Remember, you need 4 bonds around each carbon to stabilize it. So we have sodium phenoxide, so that means a sodium plus needs to be around to stabilize that negative charge. That oxygen has a full octet around it, so it's going to have a formal charge of -1 since it's only going to be singly bound. Okay, and then potassium tert-butoxide. Okay, so that's kind of a mouthful, right? We're going to have carbon, which is going to be attached to 3 methyl groups. So this oxide, alkoxide anions are what you're going to see right here. Okay, so they need to be stabilized by a positive charge. So sodium and potassium are going to be in group 1A. So that means they only have 1 electron to lose in terms of a valence shell, and they're going to stabilize that negative charge. Okay. Okay, so if I were to draw the line structure counterparts of all these compounds, I will do so. Again, hydrogens are just assumed. So this is really kind of a shorthand way of drawing everything. So this is just going to be benzene right here, as I drew it before adding those hydrogens. Again, every corner or point is going to indicate a carbon. So for this particular instance with T-butoxide, it would look like this. And then phenoxide, it's right there. That's going to look same thing as that benzene ring. But this is going to be the conjugate base of phenol, if you've ever heard of that. So phenol is used in in biochemical extraction. Okay, so this is going to be the conjugate base of it. All right, so in other words, this is going to save me a lot of time in terms of writing things out. So this course could be a lot longer if I had to do all this all day, right? Sometimes I'm going to have to do this, maybe not this particular carbon, but if I'm going to write out a methyl or something, I'll have that there, just so you have, you just get no misconception of what's there. But typically, if you're going to draw out a line structure, it's going to be a very shorthand way of showing a particular molecule without all the fluff, if you will. Because you'll see in some of these more elaborate molecules that that you'll be manipulating throughout the course, it's going to become a little bit tedious writing more hydrogen. Okay, so with the exception of this NH2 group and this CH3 group here, what is the hybridization of this particular construct? It is going to be sp2, meaning everything is going to be flat and planar from pretty much this carbon onto this carbon. Okay. Now that said, you see that there's a pi bond here, a pi bond here, a pi bond here, and a pi bond here. Okay, so with that said, we need to start pushing electrons to see if there's any type of resonance stability about this particular compound. So what we're going to do is we're going to take these electrons here, push them in, and push these electrons out. Okay, so what I'm doing here is I'm satisfying the octet about all of the nuclei that I'm affecting, and this is what is going to generate what is referred to as charge separation. Okay, that nitrogen is now going to be positively charged because it has 4 bonds about it. Okay, so notice how I didn't manipulate any of the other bonds just yet. So what we're really going to do is push one set of bonds at a time. Now, don't forget that you have another hydrogen that's sticking off of this carbon here. Again, each one of these corners represents a carbon. Okay, so there's a net negative charge here, because if we were going to do a quick formal charge of carbon, we're going to have 4 valence electrons in the ground state, minus how many bonded electrons? 1, 2, 3, 4. So 4 divided by 2. Whoops. Minus how many lone pair electrons? 2. Oh, whoops, I forgot to mention the hydrogen that's not here, so that's going to be a total of 6 actually. 6 bonded electrons minus 2 lone pair electrons, so that's going to be -1, so that's where the formal charge is going to be. Okay, so where do we move on from here? Well, we could go right back to where we started and be a little counterproductive and just show us that it's somewhat resonance stabilized, or we could keep moving here, which is what we're going to do. We're going to throw those lone pair back in right here and pick these electrons up. Okay, so notice how that charge migrates every 2 nuclei, because if you're pushing electrons, it needs to go to the next bond, and that affects the bond next to it. So now we're at this junction where there is a ketone group that's hanging off of here. Okay, so this is an amine, this is a ketone. Okay, now just a little bit of functional group trivia there. So if we were to take our lone pair and place it right there, we're going to boot these electrons out. Notice how I have the double-ended arrows there for all my resonance structures for each step. So now we have a negatively charged oxygen. So that negative charge has made its way from one carbon to another type of carbon to an oxygen. Okay, so that charge separation's still there. So we really only have one way to go, and that's back this way. But we're not going to repeat some of the other structures we've seen here. So we're just going to move forward. I'm just going to kick these electrons out. Okay, so now we have this last charge separation resonance structure. Oops. Okay. One thing to make note of here is that this resonance form and this resonant form are not the same. If you were to flip these over, it's going to look different from what you see here, right? Because this is going to be planar, and the CH3 isn't the same as that C double bond O. So, in other words, we're going to count how many resonance structures we have in the end, because the more resonance structures you have about a particular compound, the more stable that particular anion is or compound is. Anion, cation, whatever. Okay, so in this case, we've just had charge separation. You may see some ions that are polyatomic, right? And there's going to be quite a bit of drift in terms of electron movement. Okay, so now we're going back to being a stable compound where everything is where it needs to be, no charge separation whatsoever. So how many resonance structures do we have in total? 1, 2, 3, 4, 5, 6. Okay, so quite a bit. In other words, there was quite a bit of electron movement there throughout the entire ring, and even off into, let's say, this electron withdrawing group that's right here. So pay attention to all of these lone pairs that you see, okay? Sometimes, particularly when we get moving forward and into chapters 5 and 6 and so on, you're going to start to see that those lone pairs I'm not really going to draw, because those are kind of the details that you're going to have to pay attention to down the road. All right, so this is just going to be a little bit of an exercise in functional group identity. You can take a look in your table 1.6 in your text, so you can use that as a reference. I would just kind of keep that bookmarked in case you're ever shaky on what something's going to be named. Okay, in any event, let's go over a few of these, and then you can look at some of the ones and try to ID them above. This first one is going to be an alkyne. Okay. That YNE suffix means that there's going to be a triple bond about that particular structure. So that's an alkyne group or alkyne moiety. This is going to be an amino or an amine group. Okay. So not to be confused with an amide, which I'll show you here in a few minutes. All right. This is isopropanol, so this is an alcohol. So if a carbon or OH is directly attached to a carbon, that's going to be an alcohol. A simple alcohol that you could think of would be methanol or say even water. Okay? Even though we typically don't think of water as an alcohol. Okay, so we have, this is isopropanol, which seems to be impossible to find in the stores these days. So we'll put it as an alcohol. Okay, so what you see right here is what is referred to as acetaldehyde. So this is an aldehyde compound right here, or aldehyde group. So these are always going to be terminal, being that they have a hydrogen attached to it. Remember that that hydrogen should be assumed in all these line structures. I'll put all my lone pairs here so you guys don't forget. Okay, so this is going to be an aldehyde. A-L-D-E-H-Y-D-E is in Jekyll and Hyde. And then the last one on the right there is going to be a ketone, as I referred to before. So that would be 2-butanone. Okay. So 1, 2, 3, 4 would be buta. So this is a ketone. That O-N-E is very instrumental in the nomenclature, which we'll get into later on in this semester. Okay, back up to this funky looking thing we have here. This is going to be what is referred to as an amide. Okay, so amides are different from amines because you have that CO double bond that's right adjacent to that amino group. Okay, so you can have secondary amines like you see here. You can have tertiary amines if you have an additional carbon that's attached in lieu of that hydrogen there. And you can have primary amines, or amides. This is a primary amine right here. So in other words, this would be a primary amide. Okay. All right. NO2, as you've seen before, that's a nitro group. So that's nitro. Okay. This is going to be an ether. E-T-H-E-R. Okay. And you'll see some of that nomenclature in Interchapter A. And this, finally, is going to be an alcohol or hydroxyl group, whatever. Man, can I spell today? Apparently not. Okay, so don't just leave it to this to figure out what some of the other functional groups are. Again, you can look in that table 1.6 in your text. Again, I would think it would be just best to bookmark it so you have it there. If you ever need to look it up for an assignment for a quiz or an exam, I'll just pop it right open and you'll be able to ID it. All right. So I hope this was a good first intro to organic for you. Hopefully everything wasn't too overwhelming. You know, kind of take this piecemeal, watch it again if you need to, if you have the time, and try to work out some examples that I have within the text. And of course, don't forget to stop by for office hours or look over the office hours if you could not attend. I will be able to send a link to you after each particular meeting. It'll probably revolve, you know, around one or maybe two different topics that I'll kind of go into greater detail. It's not going to be a formal lecture by any stretch of the imagination, but it should help you out with some more examples, etc. All right. Thanks for watching. Have a good one.